pure substances. Let me give the definition of the pure substance like this. A pure substance is a substance of a single chemical species like H2O or nitrogen, etc. A mixture of constant composition like air, which is a mixture of nitrogen and oxygen, can be treated as a pure substance at temperatures where phase separation does not take place. Now I shall give some of the examples of pure substance. Air contained in a vessel or a chamber can be treated as an example of pure substance. Another example is liquid water. In thermodynamic equilibrium with water vapor or steam can be taken as example of pure substance. Though number of phases are 2, throughout the chemical composition is only H2O. Another example is a mixture of combustion gases whose chemical composition is same throughout can be taken as an example for pure substance. The tick mark indicates these are all pure substances. Now I shall consider another substance which is not a pure substance, that is a liquid air and gaseous air, which is a mixture under equilibrium, is not the example of pure substance because the percentage by composition of nitrogen and oxygen is different in liquid air and gaseous air. Therefore, it is not the pure substance. Now, let me define the phase. The different states, that is states of aggregation like solid, liquid and gas, in which a pure substance can exist are called its phases. If a system contains more than one phase, they are separated by a phase boundary. Now let us consider 1 kg of water in a piston cylinder arrangement, say at a temperature of 30 degrees centigrade. The piston is weightless and the pressure acting on the piston is 1 atmosphere, which may be taken as 101.3 kilopascal. Now I started giving heat to this water. What shall happen? We would not see any movement in the piston, but the temperature of the water keeps on increasing, say from 30, 35, 45 like that. The pressure is 1 atmosphere, that is constant. I kept on heating the water till 100 degrees centigrade temperature is reached. Once the temperature is reached 100 degrees centigrade, if the heating is still continued, then the movement of the piston begins upwards. Why? The reason is the vapor begins to get formed at 100 degrees centigrade, because the boiling temperature of water is 100 degrees centigrade, corresponding to the pressure of 1 atmosphere. That means at 100 degrees centigrade, the change of phase from liquid phase to the vapor phase just begin to occur, and if the heating is continued, we get a mixture of liquid water and water vapor. The temperature is still 100 degrees centigrade. The pressure is 1 atmosphere acting on the piston. If the heating is continued at the same pressure of 1 atmosphere, we get entire vapor or steam at 100 degrees centigrade. If the heating is further continued, the vapor that is formed at 1 atmosphere tends to increase its temperature, where the temperature is greater than 100 degrees centigrade. If we look at all the 5 figures, the first state is called as subcooled liquid. The second figure is known as saturated liquid. The third figure is known as wet mixture or wet vapor. The fourth figure is known as dry saturated vapor. The fifth figure is known as superheated vapor. Here the pure substance water is heated from 30 degrees centigrade till it becomes superheated vapor at constant pressure of 1 atmosphere. Now I shall define the 5 states. Subcooled liquid is the liquid whose temperature is lesser than its saturation temperature corresponding to its saturation pressure. In this case, the saturation pressure is 1 atmosphere and the respective or corresponding saturation temperature is 100 degrees centigrade. Now coming to the next definition of saturated liquid. It is the liquid at which the change of phase from liquid phase to vapor phase just begins at constant pressure and also at constant temperature. Please note that while the change of phase is happening from liquid to vapor, the pressure as well as the temperature both remain constant. In this case, the saturation temperature is 100 degrees centigrade and the saturation pressure is 1 atmosphere. Now, I define dry saturated vapor. It is the state of vapor which has just completed its change of phase from liquid at constant pressure and constant temperature. Here it can be noted that if we remove a slightest amount of heat from the dry saturated vapor, a little amount of liquid would appear. Next, I define wet vapor. It is the mixture of liquid and vapor which is in thermal equilibrium at saturation pressure and saturation temperature. Saturation pressure is the pressure at which the change of phase is happening from liquid to vapor or from vapor to liquid, and the respective temperature which remains constant during that change of phase is known as saturation temperature. To the wet vapor, if heat is being supplied, then the vapor content would increase. To the wet vapor, if the heat is rejected from the wet vapor, then the liquid content will be increasing, but the temperature and pressure remains constant. Here we shall define dryness fraction of wet vapor. It is the ratio between mass of vapor in the mixture of liquid and vapor, which is in thermal equilibrium, and the total mass of mixture. Pictorially, we can represent it as, consider a wet vapor. This is the phase boundary. Below the phase boundary, we have the liquid mass. Let it be ml. Above the phase boundary, we have vapor. Its mass be mv. Then dryness fraction of mixture is equal to x. It is indicated as x. mv divided by ml plus mv. For saturated liquid, the dryness fraction x is 0. For dry saturated vapor, x is equal to 1. Therefore, the domain of x is 0 less than or equal to x less than or equal to 1. This is the domain of dryness fraction x. Now let me define superheated vapor. It is the state of vapor whose temperature is greater than saturation temperature corresponding to its saturation pressure. For example, steam at a temperature of 110 degrees centigrade at 1 atmospheric pressure is superheated vapor. If we reject heat from superheated vapor, first it gets cooled till saturation temperature, then only condensation could begin. Now let us represent all the 5 states, that is subcooled liquid, saturated liquid, wet mixture, dry saturated vapor and superheated vapor on the temperature entropy diagram. T versus S. This is very important thermodynamic plane other than PV plane on which many thermodynamic cycles, namely Rankine cycle, vapor compression, refrigeration cycle are indicated. Now let us indicate all the states. The first state is subcooled liquid. Let me represent with a point A, small a, which when supplied with heat, temperature increases and entropy also increases, because entropy is that property which increases whenever heat is supplied, till it reaches the state B, where the change of phase is just about to begin from liquid to vapor. This state B is known as saturated liquid state. When heat is supplied to the saturated liquid, temperature remains constant, but entropy keeps on increasing because heat is supplied. The change of phase completes at state D, where the state D can be taken as a dry saturated vapor state. Between state B and state D, let me take state C, which is corresponding to the wet mixture state, which is a mixture of liquid, water and vapor, which is in thermodynamic equilibrium at saturation pressure and saturation temperature. State D is the dry saturated vapor, which has just completed its change of phase. Beyond D, if heating is continued, we get superheated vapor, corresponding to which I give a symbol E. This is superheated vapor. So A, B, C, D, E is isobar because throughout pressure remains constant while heating is done. So B to D is change of phase from liquid phase to the vapor phase. The corresponding to temperature BCD is known as saturation temperature, and the respective pressure is saturation pressure. For any pure substance like water or any refrigerant, at a given saturation pressure, there is only one fixed value of respective saturation temperature, and vice versa. That means once the saturation pressure is fixed for any pure substance, it has only one fixed value of respective saturation temperature. For example, for water, which is a pure substance, at a Psat of 101.3 kilopascal, the respective saturation temperature is 100 degrees Celsius. Here it is very important to note that for any pure substance, as the saturation temperature increases, saturation pressure also increases. And vice versa. That is, as Psat, that is saturation pressure, increases, implies Tsat also increase. For example, the boiling temperature of water increases with pressure. Example, in pressure cooker, the boiling temperature of water would not be 100 degrees centigrade. It is definitely more than 100 degrees centigrade because the pressure in the cooker is more than 1 atmosphere. And as the elevation increases above the mean sea level, the boiling of water would not occur at 100 degrees centigrade because the pressure of atmosphere keeps decreasing with the elevation. At higher elevations, the water might boil at a temperature much lesser than 100 degrees centigrade. For example, on the Mount Everest, water may boil at 40 or 50 degrees centigrade because the pressure at Mount Everest is much lesser than the pressure at main sea level. So, as the saturation pressure decreases, saturation temperature also decreases for any pure substance like water or refrigerant. Now, let me define latent heat of vaporization. It is the amount of heat required to convert 1 kg of saturated liquid into 1 kg of dry saturated vapor at constant pressure, that is saturation pressure, and also at constant temperature. It is indicated as L in kilojoule per kg. L of water at 1 atmospheric pressure is equal to 540 kilocalories per kg, which is equal to 540 into 4.187 kilojoule per kg. Here it is very important to note that as Psat, that is saturation pressure, increases, Tsat also increase, but latent heat of vaporization decreases. Let us give the important symbols of properties like saturated liquid enthalpy, saturated liquid entropy, dry saturated vapor enthalpy, dry saturated vapor entropy, like this. Important symbols or notations. HF is saturated liquid enthalpy at Psat and Tsat. SF is saturated liquid entropy at Psat and Tsat.